Continuing with our example of Francis Galton's data set, to better understand what's going on, it's useful to visualize our regression models. So this is a simple linear regression model overall using Galton's measure of mid-parental height. So using his measure of mid-parental height, we get a coefficient of 0.40. That tells us for every 1 inch increase of mid-parental height, this combined measure of mother and father's height, we expect children's height to increase by 0.40 inches. The intercept tells us that when mid-parental height is 0, we expect children to be roughly 39 inches tall. The model, including both mother's height and father's height, looks like this. Right? This is the equation for that plane. The equation for that plane has an intercept, 2 slopes. Right? Specifically, we would interpret the intercept as follows. When mother's height is 0 and father's height is 0, the expected height of children is 22.3 inches. For the father's height slope, we would interpret it as follows. For every 1 inch increase of father's height, we'd expect children's height to increase by 0.38 inches, holding constant mother's height. For every 1 inch increase of mother's height, we would expect mother's height, for every 1 inch increase of mother's height, we'd expect children's height to increase by 0.28 inches, holding constant father's height. The idea is that the partial regression coefficients, they're interpreted in terms of holding constant the other variables or inputs in the model. And of course, the intercept is when both x1 and x2 are equal to 0. Now we can further explore what these regression coefficients mean by investigating this visualization of multiple linear regression. It's just a plane. When you have 2 variables, it's just a plane fit through a 3D scatter plot of data. Right? It's still fit using the method of least squares, just like simple linear regression. It's still minimizing the sum of the squared errors. The slopes or partial regression coefficients are now edges on the plane. The intercept is the point on the plane when both inputs are set equal to 0. So let's look at this, okay? So the intercept here is 22.31. It's located right there. When the heights of both parents are 0, we expect the height of the child to be 22.3 inches. That point on this graph, that is where the intercept is located. Right? That's the point in the graph when father's height is 0 inches and mother's height is 0 inches. That's not that substantively meaningful. In fact, you can see the scatter plot. It's not really that close to that intercept. That's because everybody at least has a parent that's greater than 0 inches tall. But we can also rotate the graph and look at the edges of the plane to understand and interpret these partial regression coefficients. Okay? So here we have the slope. Okay? This is just the rise over the run for father's height. Okay? What this tells us, right, is that for 1 unit increase in father's height, we expect the height of the child to increase by 0.38 inches, controlling for mother's height. That appears as this edge on this side of the graph. Okay? So for every set of increases, for the run and the rise, okay, that ratio of the rise over the run is 0.38 inches. For every 1 inch increase of father's height, we'd expect children's height to increase by 0.38 inches. That's just that edge. Okay? That's the slope of that edge of the plane. Right? For a 1 unit increase in mother's height, we expect the height of the child to increase by 0.28 inches, controlling for father's height. What that means is we're just looking at this edge of the plane. You can see this edge of the plane. It's a little bit less steep. Okay? That reflects the fact that the slope for mother, the partial regression coefficient, is 0.28. It's not 0.38. So the slope on this edge of the plane is a little bit narrower. Okay? It's a little bit less steep. But again, it's just the rise over the run for this part of the slope, for this edge of the slope, which you can visualize this way. Right? For every 1 inch increase of mother's height, we expect children's height to increase by 0.28 inches. Just that edge of that plane. Now you might say, well, what happens if you have more than 2 inputs? Right? Well, you can put more inputs into your regression model. You can put not just mother's height and father's height, but you can put the number of kids in your family. You can put parental education. You can put lots of input variables, lots of predictor variables into your regression model. This is why multiple linear regression is a very flexible model. We can use it in many different contexts because we can put many different variables on that right-hand side of the equation. More generally, we can add k number of inputs on the right-hand side of the equation. Right? So we have y equals y hat plus the error term, where y hat can be k equals whatever number of inputs. You can never have more inputs than the size of your sample in classical linear regression, or in terms of the model that we're talking about here. But for this data set in which we have 800 respondents, you can include quite a few predictor variables, input variables. The interpretation of the output from statistical software, it's basically the same as with two inputs. You still have to interpret the partial regression coefficients in terms of controlling for or holding constant the other variables in the model. The intercept, again, is when all of those x variables are equal to 0, when all those k different x variables are equal to 0. One difficulty is that it's more difficult to visualize beyond two inputs in the regression model. And we'll look at that in just a moment.